Hey folks, welcome to your first set of Chemistry 1 video notes. Today we're going to be talking about the basics of chemistry and lab safety. Let's get started. So first off, what is chemistry? Chemistry is the study of matter. What's matter? Nothing. What's the matter with you? Matter is defined as anything that has volume. In other words, it takes up space. And it has a mass. So, in essence, chemistry is the study of, well, basically everything. Before we get too far, we should make an important distinction between mass and weight. Mass is a measurement that simply reflects how much matter there is. It's not dependent on anything else, just how much matter there is. The mass of an object on Earth will have the same mass in any other place in the universe, regardless of gravity. In science, mass is often measured in kilograms or grams, and we use a balance to make that measurement. We never say that we're going to weigh an object in science. We say we're going to measure the mass of the object, or we're going to mass the object. It sounds a little weird, but that is the most correct way to talk about it. Weight, on the other hand, is dependent on gravity. You'd weigh significantly different on the moon than you do here on Earth, because the moon has a different amount of gravity. In fact, on the moon, you weigh about 1/6 the amount that you weigh here. We use scales to find the weight of objects. In this class, we'll only ever use mass, so we'll only ever use balances. Back in the day, we used to use triple beam balances like this one. To make our lives a little easier, we'll be using digital balances that measure to the 10th or 100th of a gram like this one. In more advanced chemistry classes, you may use an analytical balance, like this one, that measures to the 10,000th of a gram, or 4 decimal places. Okay, that's enough matter talk for today. Let's talk about how and why we do science. Throughout the year, I want you to always keep in mind that a good scientist is objective and performs replicable experiments. To be objective, you must be data-driven. Your questions about the world come from a natural curiosity, but the answers to those questions must be supported by scientific data. You should never, ever draw conclusions based on opinions, preconceptions, or feelings. Nor should you ever decide to perform an experiment simply to confirm your own biased thought. Questions about the world should be very open and testable, and you must have an open enough mind to change the way you think about the world when you're presented with data that contradicts your own understanding. We do science to seek out truth. As simple human creatures, we may not ever know the full truth of how the world works. But as we learn, develop technologies, and evolve as a society, we can find better, more complete answers. There are many examples, as we'll see later this year, where new scientific evidence led to new discoveries that completely shook humanity's understanding of the world. Science never lies. It presents the fullest truth it can based on its limitations. So, scientists must be objective, and their experiments must be replicable. A scientist with a breakthrough discovery who doesn't bother to share with the scientific community how they perform their experiment, or they can't reproduce their own experiment, will not be taken seriously. If you want your research to be taken seriously in the scientific community, you publish a paper about it. In this paper, you explain some background information about the purpose and results of your experiments. You explain all of the materials and processes you use to perform your experiment and collect data, and you explain what you did with that data to draw the conclusions that you drew. This paper gets sent out to the appropriate scientific journal, and other scientists review it, poke holes in it, tell you how you can perform your experiment better, try your experiment themselves, and attempt to get similar results. And either they approve or reject the publication of your paper. This quite rigorous process is called the peer review process, and it helps to ensure that scientists are communicating actual scientific information, and not biased or sensational information that's false. So why do we do science? Because we have a lot of questions about the world. Humans are naturally curious beings, and we want to learn. Contrary to the very linear and boring scientific method that we used to teach when I was in school, the scientific method is very fluid, circular, and there's no right or wrong way to go about it. We generally start with making observations, where we notice something about the world. After noticing that something, we tend to ask questions about why it works that way. We then come up with some guesses or hypotheses about why it works that way. These hypotheses are answers to our questions that can be used to predict how something behaves. We then develop experiments that can test those predicted behaviors. Next, you perform those experiments and collect data from it. Then you take that data and analyze it and decide whether your hypotheses make sense or not. We can then go around and around in circles, altering our answers to the questions based on our data and testing our answers again and again until we're satisfied that our answer is correct. Once we're satisfied with our answer, we can reword that answer to fit in with current general theories. You may have learned this before, but it's important to make sure you remember that a theory is an explanation for why something works the way it does. Scientific laws are these simple observations that say, hey, this thing happens consistently. Theories come in and explain why those things happen the way they do, and that's where the real work of scientific research comes in. As our technology advances, we can perform better tests and make new, better observations that may work their way through the scientific process and help us to determine better explanations or theories. This is why I was very careful earlier to say that science is the search for truth, not that it is truth. It's the best truth that we have, but it's completely changeable based on what tools and minds we have at our disposal. So you've had a few years of general science classes, and you should know by now that basic information about how and why we do science. You're in this class to learn chemistry, so let's talk about chemistry. As we said, chemistry is the study of matter. There are all sorts of types of matter and ways to analyze them, so we generally branch chemistry off into 5 different branches, each with their own specific purpose, but together they make up the whole tree of chemistry. Organic chemistry, a truly awe-inspiring and difficult college class to take, is only concerned with chemical compounds that contain carbon. These compounds are things like pharmaceuticals or fuels. Inorganic chemistry is focused on all the other chemicals, the ones that do not contain carbon, like minerals, salts, semiconductors, metals, and nonmetals. Inorganic chemistry was probably my 3rd favorite chemistry class in college. It talks a lot about the structure of atoms and how and why they bond together to make molecules. Physical chemistry, my favorite class from college, mostly because it's very math-oriented and my professor was great, is very similar to inorganic chemistry, but it's focused a lot more on the behavior of matter and its changes. Physical chemistry is important when we talk about energy and how much energy we can get from a chemical reaction. Or if I'm a company in charge of making a certain chemical, I'm going to be concerned with how efficient my process can be. So I may want to increase my reaction rate or how fast the reaction occurs. Analytical chemistry, I'll say it's tied for 3rd favorite, is all about what substances and mixtures are made of. Analytical chemistry is extremely important for our safety. One example of an analytical chemist is one that studies water quality. They determine the amount of different substances that are mixed in with our water and whether it's safe to drink or not. Analytical chemistry is also very math-based, but you have to be very good in the lab to do it well as an analytical chemist. Finally, biochemistry, my 2nd favorite chemistry class in college, is solely focused on matter and reactions in living organisms. This overlaps a little with organic chemistry because all organisms are made of carbon-containing compounds. But it's generally focused less so on the individual structures and more so on the function of the molecule, or what those molecules do in your body. All 5 of these branches are very important for the whole picture of the chemical world, and they're all very useful in their own different ways. Well, now that you know some of the basics about science and chemistry, you're ready to learn about the tools you'll need in this classroom. We may not use all of the following pieces of equipment, but it's important to learn about them as they're the most commonly used in the chemistry class. First and foremost is the beaker. It looks like this, and it's used to hold stuff. It has measuring marks on it, which we can use to get a rough estimate of how much of the liquid we have, but generally we do not use it for accurate measurements. We often perform reactions in a beaker. Another piece of glassware to perform reactions in is an Erlenmeyer flask. This is best used for reactions that produce bubbles or need stirred. The shape of this flask helps ensure that we're not splattering chemicals all over the place, as we might with a very open-top beaker. A Florence flask can be used about the same as an Erlenmeyer flask because it has a really long neck that will help prevent spillage. Now, onto the glassware we can use to measure the volume of liquids. A graduated cylinder looks like this. It's important to remember that we always measure from the bottom of the meniscus when we use a graduated cylinder, or any of the following liquid measuring devices. The meniscus is the curved part of the liquid. Due to surface tension, liquids naturally curve up the sides of cylindrical glassware. We want to make sure that we are measuring at eye level from the bottom of that curve. To be even more accurate with our measurements, we could use a pipette and pipette pump. You use the pipette pump to suck liquids up into the pipette up to the desired volume, and then release those liquids into the desired vessel. These are much more accurate than graduated cylinders, but they take a lot more practice and a lot more time, since the biggest pipettes we have in our classroom only measure up to 25 milliliters at a time. Lastly, we have the burette. This is best for reactions in which we are adding a to-be-determined amount of liquid to another liquid. We fill it all the way up to the 0 mark at the top, and then use the valve at the bottom, which is called a stopcock, to release the liquid. We often use this for titrations, when we're looking for color change in our reaction. When we've added enough of the liquid from the burette, we shut the valve off and read the volume as it is. Then we take our initial volume and subtract that from our final volume to see how much liquid we used from the burette. If we're not so concerned with measurements, but we just want to add a few drops, we use a pipette or dropper. Test tubes look like this, and we use them for holding smaller amounts of liquid or performing smaller experiments. Reaction plates or well plates look like this, and we use these to perform multiple small-scale reactions at a time. A glass stirring rod is just a rod of glass, and we use it to stir our reactions in a beaker. A funnel looks like this, and we use it to safely transfer liquid from one vessel to another. A mortar and pestle, my personal favorite, looks like this, and we use it to crush up crystals into a fine powder. A crucible looks like this, and it's often used over a fire to melt chemicals or to dry them out. Lastly, an evaporating dish looks like this, and it can also be used to dry out wet solids over a fire, or to evaporate water from a solution so that you can isolate the compound in solution as a solid. The following are some tools that you'll need to use in this class. A hot plate looks like this, and it's used as a surface to heat things up on. We often set beakers or flasks on them. Some come with 2 knobs. The second knob runs a revolving magnet that's under the plate. We can put a small magnet, which kind of looks like a pill, in our flask or beaker, and it'll spin when you have the stir knob turned on. This frees up one of our hands so we don't have to manually stir with a stirring rod. An electric or digital balance looks like this. We never ever put chemicals directly on the balance. Instead, we'll use a weighboat, which you'll see later, or a beaker or a flask. We set those on the balance and then press the 0 or tare button before you add chemicals to be massed. This makes the balance read 0 with the vessel on top, so anything else you add to it will be the only thing that's measured. An analytical balance, like this one, is used the same way, but it's very sensitive, so it has a series of sliding doors around it that you can shut and block any wind from affecting your measurement. This is the test tube holder, which we can use to carry test tubes, particularly hot ones. A test tube rack is used to hold multiple test tubes at once. Most even come with pegs on the back of them so that you can set your freshly cleaned test tubes upside down to dry out. A test tube brush is a small brush that you can use to clean test tubes or smaller pieces of glassware or equipment. A beaker brush is a large brush that can be used to clean beakers or larger pieces of equipment. When in doubt, go with the test tube brush. If you force a beaker brush into a piece of glassware that's too small for it, you'll end up breaking the glassware. This is a weighboat, which we use to hold our solid substances when measuring them on a balance. This is a scoopula, which we use to scoop solid substances out of their containers. These are beaker tongs, which can help us pick up hot beakers. We probably won't use these since I only have a few, so if you have a hot beaker that needs moved, let me know and I'll help you out. These are called crucible tongs, which are meant to hold crucibles when they're hot, but honestly I use them to pick up all sorts of things. This is a Bunsen burner. It's where we get our fire. We'll definitely use these this year. It's important to listen and follow directions when using these so that you don't get injured. This is a striker, which is used to create sparks to start the fire in the Bunsen burner. We do not strike these to create sparks for fun or because we like the sound. The flint piece that makes the spark is expensive to replace, so please don't play with these. A hot pad like this one is used to sit hot glassware on. Never put a hot piece of glassware directly on the cold black tables in our classroom, as the drastic temperature change can shock the glassware into shattering. We use these insulating hot pads so that we're not directly putting the glassware on the tables. This is a ring stand which holds all sorts of different clamps. Think of it like an extra pair of hands. It holds glassware so you don't have to. The 2 most common clamps we'll use in this class are utility clamps, which are best for test tubes but will hold a lot of things, and burette clamps, which are specifically designed to hold a burette. We'll be sure to talk about lab safety for each and every lab that we do in here, but here are some of the most important and basic ground rules. Always wear your safety goggles until everyone is finished with the lab. You never know what accidents can happen, even if you're not near the chemicals being used. I don't want you to get chemicals in your eye because then I have to fill out an accident report. Never ever consume food or drink in the same place chemical experiments have been performed. If we're using an open flame, make sure any long hair is pulled back. I do have unused hair ties available if you need them, and that your sleeves are not baggy. Also, be careful not to place the open flame directly under the wooden cabinets. On lab days, we must always wear closed-toed shoes, never open-toed sandals like flip-flops. Failure to do so will result in you wearing gloves on your feet for protection. If any glassware gets broken or chemicals get spilled or somebody gets hurt, immediately notify me by saying Code 1 loudly. Do not scream at me or panic, but don't just say my name. Code 1 lets me know that there's an actual emergency that I need to attend to immediately, and it's not just that you're impatient with the question. After every lab, be sure to wash your hands thoroughly with soap and water. Soap is provided at each sink. Also, after any lab that uses glassware or tools that get dirty, be sure to wash the glassware or tools with dish soap provided in these smaller bottles at each sink, and hang them up to dry on the drying racks. Well, that's all for today, folks. Please study your pieces of lab equipment, lab safety rules, and basics of chemistry so that you're ready for our first quiz. Please be sure to let me know if you have any questions.